Hello and welcome to another instalment of quantum mechanics. Before I give you the overview of today's class, let me just briefly recap where we are regarding the general theory of angular momentum. So in the context of the general theory of angular momentum, we would consider a linear operator, a linear vector operator J, which has three components, three Cartesian components, Jx, Jy and Jz. These things are going to be, or are, by demand, Hermitian. Any set of three operators, which are linear and Hermitian, in other words, they equal their own daggers, and which obey the Lie algebra that I'm about to write down, are spoken of as angular momentum, general angular momentum operators. The Lie algebra is that Jx and Jy, their commutator is IH bar Jz. And then similarly, two more expressions, which follow by cyclic permutation of x, y, and z. So x becomes y becomes z, y becomes z, z becomes x, z becomes x, x becomes y. So any set of three linear Hermitian operators that obeys this Lie algebra is an angular momentum in the general sense of the term. We stated without proof two particular key results in equations 217 and 18 respectively. The first of these equations said that the the generalised angular momentum could have only integer or half integer values. In this sense of the term, equation 218 said that m, the generalised magnetic quantum number, varied between minus j and plus j in steps of 1. Here we had generalised spherical harmonics, which were eigenfunctions of both j squared and jz. And the eigenvalues of these operators were respectively written as the j that appears here, and mh cross, respectively. Lastly, I'll mention that we introduced operators, raising and lowering operators j plus and minus, as certain linear combinations of the jx's and jy's, and that these raising operator j plus would increase the m value of a generalised spherical harmonic by 1, and j minus would drop it by 1. So this is just some background revision. But one unsatisfactory thing, one thing that made us sad, temporarily at least, was that I didn't prove these expressions, 217 and 18. That's one of the first things that we'll do in concluding our discussions on general angular momentum. In fact, the two things that we'll do to knock off section 33 are to prove these results. Secondly, we'll make a link between the theory of matrix mechanics and angular momentum. Matrix mechanics we learned about earlier, angular momentum we're learning about now. We're going to develop a matrix mechanics theory of angular momentum in section 34. Lastly, we'll apply our results to the theory of spin in quantum systems. So let's begin with the proof of equation 218, this idea that the magnetic quantum number m, can take any value between minus j and plus j in steps of 1. We need to prove this. We need to prove equation 218. And again, this is being done in a representation-free way, using nothing more than the Lie algebra of the Hermitian operators, Jx, Jy and Jz. So to begin with our proof of 218, I just want to begin by writing down the squared angular momentum, which we know from Pythagoras' theorem in essence to be the following. Now I could take the expectation value of both sides of the equation. Now the expectation value of a sum of operators is going to be the sum of the expectation values. So I can do this. What I want to now prove is that each term on the right-hand side is a non-negative real number. So each term here on the right-hand side is a non-negative real number. So to prove this, let's consider, for example, the expectation value of the first term on the right side of this expression. The expectation value of jx squared. You'd sandwich, I'm using Dirac notation here, the operator jx squared in between two si's. Since j is Hermitian, it's a frog that can hop from left to right without change. So I've just made use of the fact that the j's are Hermitian. If you're to write this Dirac bracket explicitly, it will be the integral of the first slot starred times the second slot, this star times this, which is the magnitude squared, integrated over all space, which is manifestly non-negative real number. Similarly for the second and third terms on the right side of the equation at the bottom of the first board. So what we learn is that the expectation value of j squared is the sum of expectation values, each of which are real and non-negative. Now, if I were to discard two of these terms, for example, the resulting real number must, in general, be smaller. So if I was to discard the jx squared and jy squared, I'll get a right-hand side which is in general less than or equal to what it was before, hence this equation, which is 225. So this gives us the following chain of logic. Let's take this as a starting point. Let's calculate this expectation value for a generalised spherical harmonic. So for a generalised spherical harmonic, the expectation value on the left-hand side will be written as follows. Right-hand side, similarly. But this is an eigenket of this object. When this operator acts on this, it pulls out the eigenvalue. Similarly for jz acting on the eigenket. Similarly for jz acting on the eigenket. So the left-hand side, this will pull out a factor of the relevant eigenvalue. Here, if jz were to act once, it will pull out the eigenvalue mh cross. But since it acts twice, it pulls out that eigenvalue squared. So to continue, I know that this is a number, and this is a number, and those numbers can come out the front. So we'd get a j into j plus 1. You'd be left with a bracket of jm with jm. You'd be left with this object. But I'm going to assume that these things are orthogonal and normalised, so this will equal 1. Yep, the ket analogue of a unit vector. So the bracket of jm with jm is 1. It's left, it can be discarded. Similarly with the right-hand side. Cool. I'm now going to take the square root of both sides of this expression. So mh cross squared becomes mh cross. So, sorry, there's a h bar squared here that I'm going to cancel. So now taking the square root, the right-hand side will become the magnitude of m. This is a crocodile. It knows to eat the bigger thing. The bigger thing is here. The bigger thing is now on the right-hand side, so the crocodile turns around. We've taken the square root of both sides of the expression, and so we get this. Now this is already good news. This is equation 226, because it shows that there's an upper bound on the modulus of m. The existence of an upper bound on the modulus of m is certainly consistent with 218. So since there is an upper bound on the modulus of m, there must exist both a maximum and a minimum value of m. So let me denote the maximum value of m by m max, with m min denoting the minimum value. The existence of these things again follows from the existence of an upper bound on the modulus of m. And since that upper bound depends on j, in general, the maximum and minimum values of m will also depend on j. We need to now prove that M max equals J, and we need to prove that M min equals minus J, consistent with this. So let me begin with a very emotive sounding statement. I'm going to construct this object. It's not any old generalised spherical harmonic. It's a generalised spherical harmonic Jm, whose m value happens to be the maximum. So Jm max. I now want to apply the raising operator, J plus. Now we know that J plus will act on any particular generalised spherical harmonic and raise the m value by 1. Yep. So we learned in the last class that if J plus acts on some particular generalised spherical harmonic, what you get up to constant proportionality, which we'll discuss soon, is that you raise the value of m by 1. Now there's an implicit comma here, there's an implicit comma here. You raise the value of m by 1. But here I've got m being its maximum value, and we learnt in the last class that J plus raises the value of m by 1. So that's what we proved, so let me write it down. Yep. But that's a logical contradiction, right? M cannot be bigger than its maximum value. You're rescued by the fact that there's a constant proportionality here, and the only way that I can rescue myself from logical contradiction is to make the constant proportionality naught. Now when I take something and multiply it by naught, this is a physical state. Never mind the fact that it couldn't exist. This is a physical state. But since I multiply by naught, that right-hand side has disappeared. So the technical language that's used is that this operator annihilates this state. So that's the technical language. Again, fairly strong language, but that's what it is. J plus annihilates this state, because anything else would be a logical contradiction. This is not just zero as in space filled with nothing. This isn't even a physical state. This is absolute nothingness, right? There's no physical state here. This is nothing, as opposed to empty space. This is nothing at all, so it's total annihilation. This object annihilates this one. So we take this equation as a starting point, and we pre-multiply both sides by J minus. Again, what we're trying to prove is that m max equals J. So I've pre-multiplied both sides by J minus. And at this point, we remember the toolkit, equations 220 A, B, and C, this toolkit of tricky identities that we derived in the last class. And one of them is an expression for precisely this, for precisely J minus J plus. And it's equation 220b. So equation 220b can be used to expand this object. So 0 equals J minus J plus. And if we use 220b, we could rewrite that as J squared minus JZ squared, etc. So this all equals naught. Now this is a useful expression to have because this is an eigenfunction of both J squared and JZ. Yep. So the J squared is going to become J plus 1 H cross squared. And I'll factor out the H cross squared. JZ, if it was to act once, would pull out an M H cross. If it acts twice, it'll pull out an M squared H cross squared. H bar JZ. JZ pulls out an M H bar. The two H bars get together, go at the front. We get the following. Now, since this equals naught, and since this is some particular ket, this object here must vanish. I've made one small mistake, which is to pick up a bit of chalk that's cardboard. M here is not any old M, it's M max. So this M needs a max subscript. So when we demand that what's in square brackets vanishes, we'll get a quadratic, and you can solve that quadratic using the quadratic formula. And you'll get two values for m max. Choose the bigger value for m max, and what you'll find is that m max equals j, precisely what you wanted to prove here. So that's good. We've proven that m max equals equals j. Now we took this equation as a starting point in order to show that this is true. If instead you were to begin with an analogous equation, that, using the same logic as given earlier, this eigenket with minimum magnetic contour number must be annihilated by the lowering operator, pre-multiplied by j plus, use equation 220b, continue, in other words, do exercise 59, and what you'll find is that this is true, that m min, I'm leaving the steps out, it's exercise 59, you'll find that m min equals minus j. So the minimum value of m is minus j. We know that j plus can increase the value of m in steps of plus 1. But eventually you'll get to j, which is the maximum value of m max, in which case you stop. So we've just proven this equation here, which is precisely the equation we wish to prove, namely equation 218. So this is good. Now I want to prove equation 217. Namely that the allowed values of generalised angular momentum are either non-negative integers or non-negative half integers. Physicists will often be loose and just say that j is integral or half integral. Strictly speaking, it's non-negative integers and half integers. Again, I emphasise just how profound this result is, because a special case of this, general angular momentum, is spin angular momentum. And so this is a special case, and this tells us that the spins, if I could use the loose physics language, this tells us that the spins of all physical particles, known or unknown to physics, must be either integral or half integral, an incredibly profound result. The derivation of this is almost disappointingly swift, but we should view this for its wonderful elegance. So again, let's have a ladder of allowed magnetic contour numbers m, and let's consider a particular generalised eigenket, Jm. Now in the notes I say that m is neither its maximum nor its minimum value. Let me drop that. M can be any allowed value, according to equation 218. Now we're going to keep applying the raising operator. We know that if you apply j plus to this, that the value of m will increase by 1. If you're at the top, you can't go any further, that's fine. The number of hops is going to be 0. Yep, so j plus raises the value of m by 1. And let's hop a total of p times. We're going to hop a total of p times. So this is p hops. P is an integer, and p hops is going to be the number of hops, which will take us to the maximum value of m, which we know to be j. So I can call that jj. So I'm at a particular state, little m, and a total of p hops will take me to the top. Similarly, a total of q hops will take me to the bottom, which is j minus j. So p hops take me to the top, and q hops take me to the bottom. So I start off with my magnetic contour number, little m, and p hops, each of which raises it by 1, takes me to the top. I start off with the same magnetic contour number m, and q hops take me to the bottom. So m reduces by q, and you're at the bottom. Now if we take these two equations and subtract them, m minus m vanishes, p minus minus q is p plus q, and that equals 2j. Let me divide through by the 2. Now since p and q are non-negative integers, then p plus q on 2 will be precisely this set of numbers. So we've just shown that using almost disappointingly trivial algebra, we've just shown that the allowed values of j, are the following. This proves equation 217, and there's a special case of this year 9 maths. There's a special case of this year 9 maths. All material particles have spins that are integral or half integral. Again, this is a world of pure algebra. When you're doing the general theory of angular momentum, there's no calculus. There's nothing more than algebra. And this is a setting in which we're working. I now want to move on to matrix mechanics, so section 34, the connection between matrix mechanics and angular momentum. Now, when we first did matrix mechanics, it was viewed as an alternative formulation of quantum mechanics. Yep. You could choose to represent, for example, a wave function psi as a function of position and time. You could have your operators, which were linear differential operators. And you could have your equations, which were going to be differential equations. This is in the context of wave mechanics. We took wave mechanics with its operators, its wave functions, and its differential equations. And we showed how it could be transformed to a different representation of quantum mechanics, where the wave functions became column vectors. Yep. Remember the eigenfunction expansion. Coefficients Cm, eigenfunctions psi m. So the bunch of coefficients is what represents the wave function. You're representing wave functions with a set of coefficients. And that set of coefficients Cm, which represents the wave function in the matrix theory, is a column vector. So instead of a function, you have a vector. Okay, it's infinite component vector, so you have an infinite dimensional vector space, so that's fine. Operators, differential operators became matrices. And while we never wrote down the corresponding differential equations, we did. The differential equations become matrix equations, or systems of linear equations. So this a connection that I've mentioned many times between theory of linear differential equations and the theory of linear algebra. Now, when we're doing wave mechanics, this was an alternative formulation of wave mechanics. When we're doing spin, you can't do this for spin. So one of the points of doing matrix mechanics is that this formulation is not possible with spin. You have point particles, they can't be viewed as swirling around in three-dimensional space. Hence, despite the misnomer spin, you can't think of an extended object spinning in space. And so when you're thinking of spin angular momentum, you're dealing with the spin angular momentum of point particles. And so they can't be visualized as something which extends in space. And if the spin degree of freedom in some sense is not extended through space, then you certainly can't differentiate with respect to space. You won't have differential equations for spin. On the other hand, it can be very readily, one can write down a matrix mechanics formulation of angular momentum, which is the purpose of this section. All right, so I'll just remind you, as far as matrix mechanics was concerned, if we had some linear differential equation of, say, this form, where phi and psi were two different wave functions. Sure, if phi equals a constant times psi, then you've got an eigenvalue equation, but in general, linear operator acts on function to give new function. We learned how to represent this as a matrix equation. Yep. So psi was represented by its bunch of coefficients Cm in its eigenfunction expansion. Phi was represented by its coefficients d1, d2, etc. in its eigenfunction expansion, and A, the linear operator A, was represented by a matrix, the elements of which, the matrix elements of which were A1, 1, A1, 2, A21, etc. And this was an infinite dimensional matrix. And so we learned the expression for the matrix elements. The matrix elements were given by equation 171, which I'll just write down here. The elements of the matrix, A subscript Pm, were obtained via a certain Dirac bracket, where you put the pth eigenfunction here, the linear operator A there, and the nth eigenfunction here. So this is how to get a matrix formulation of quantum mechanics, which is essential for the theory of spin. So since we're seeking a matrix theory of spin, we need to represent our operators as matrices. Yep. What are our operators? Well, in the general theory of angular momentum, our operators are j squared, jx, jy, jz. We've also got j plus and j minus. So these are the operators we need to work with. And since we're doing a matrix formulation of the theory of spin, we need to work out the matrix elements of these spin operators. So we need the matrix elements. Again, there's nothing but algebra in this world. So let's begin with the matrix elements. Let me abbreviate that as ME. We want the matrix elements of j squared. So I've revised how you calculate a matrix element. If you want a matrix element of an operator, in this case j squared, you just sandwich it between the basis vectors. What are the basis vectors? They're the generalized spherical harmonics. So here's one generalized spherical harmonic, and here's a different generalized spherical harmonic. Sure, in the bottom right of the top board, I indexed my eigenfunctions with a single number, p. Here I have two numbers, so this is like the p, this is like the m. So these are the matrix elements. Okay, sure, this matrix is going to be described by four numbers, so it's like a four-dimensional matrix, that's fine. We need to calculate this thing. Now, this is an eigenfunction of this. J squared is just going to spit out the numbers j plus 1, h cross squared, which can come out the front of the resulting bracket. What you're left with will be j prime m prime and jm. Again, these generalized spherical harmonics are orthonormal. They're orthogonal and normalized. This thing will only equal 1 if the left and right hand sides are equal, if j equals j prime and m equals m prime. I would write that using the Kronecker delta notation as follows. And this is a four-dimensional diagonal matrix. Next, we want the matrix elements of jz. Now, the logic here is going to be very similar. Yep. This is the operator whose matrix elements you want. You sandwich it between two different basis vectors, jm and j prime and m prime. Cool, we work this out. This is an eigenfunction of this, an eigenket more precisely. This is going to pull out mh cross, which comes at the front. You're left with a bracket of j prime, m prime and jm, which will give this again. Another diagonal matrix. These are equations 238 and 239 respectively. Now we want the matrix elements of j plus and minus. Things are going to get a bit harder now. Now I'm going to begin the calculation of the matrix elements of the j plus and minus operators by not calculating the matrix elements. I want to calculate a preliminary result, equation 240. We know that the j plus operator, when acting on our generalized spherical harmonic, raises the value of m by 1. we know that j minus lowers it by 1. But I want these sets of jm's to be orthogonal and normalised. Just because m is raised or lowered by 1 by j plus minus doesn't mean that this resulting right-hand side is normalised. So there's going to be some number out the front, some normalisation factor, and there'll be a different normalisation factor for the plus and minuses in general, and that normalisation factor may depend on both j and m. Whether it does depend on plus minus, whether it does depend on j, whether it does depend on m is to be determined. The point is that there's a normalisation factor, some number here, some constant proportionality, which I alluded to earlier. So our first step is to calculate this thing. So let's calculate this normalisation factor. And to begin with, let me take this expression and take its Hermitian conjugate. Now, Hermitian conjugation is a generalisation of complex conjugation. When you complex conjugate a function, you replace all i's with minus i's. When you Hermitian conjugate an equation, you replace all complex numbers with their complex conjugates. You turn all kets into bras and all bras into kets. Yep. And you replace all operators with their Hermitian conjugates. Just to repeat, when you Hermitian conjugate equation, replace the number I with minus I, replace all linear operators with their daggers, their Hermitian conjugates, and you interchange bras and kets. So j plus minus will become j plus minus dagger. The bra, jm, will become the ket. So the ket jm will become the bra, jm. Now this operator can be considered to act to the left. Just as a point of notation, you can put an arrow up here if you want, but it must act to the left because there's only a function on its left. Similarly, the ket on the right-hand side becomes a bra. And the number n becomes its complex conjugate. In general, this number will be complex. Now let me take this equation. Let me multiply these two equations first. The left-hand side of this times the left-hand side of this will give jm, j plus minus dagger, j plus minus, jm. And the right-hand side will be j, m plus or minus 1, n star n, which is the same as the magnitude of n squared. Since I'm running out of board space, let me just write it like this, and then the ket. Now I want to stare at this thing. What is j plus dagger? As a quick 1-minute exercise, you can convince yourself that j plus dagger is j minus, and j minus dagger is j plus. So hence the change I've just made. Good. This is a number which can come out the front. This is a member of the toolkit of equations 220. Yep. It's a member of the toolkit of equations 220. Now I'll put that fact to one side for a moment. Here I'm factoring out the n squared, and when I pull out the n squared, I'll get j n plus or minus 1 bracketed with itself, which is 1 because these things are normalised. So let me take the square root of this expression, and I end up with the magnitude of n. Yep, the magnitude of n. Now there's a certain freedom here. I want to make my life as simple as possible, right? This could be a complex number, and the square root of this expression would give me the magnitude of that complex number. But let me decree that n is going to be real and non-negative. So when I take the square root, I actually get n itself by decree, just to make my life simpler. There is a loss of generality here, but it's trivial. All right, so we've got an expression for n, which is going to be the square root of this. And when I see this product of operators, I think there's an element of my toolkit that lets me expand this object, and that is 220b. So we're at equation 245 now. So if I now use equation 220b, I can write out an expression for j minus plus times j plus minus, and what it is j squared minus jz squared plus or minus, sorry, minus or plus h bar jz. That's good. Now at the beginning, some of the tricks I pulled seem to be, where the hell did they come from? But now you're starting to see the same thing used again and again, and I hope that the tools that I'm using are going from being something which is unfamiliar and bizarre to something which is natural. There's only a very limited number of tricks. What I've written at the top of the middle panel board, the Hermitian character of jx, jy and jz, the definitions of j plus and j minus, and the toolkit, equations 220a, b and c. That's all you got to work with, right? So if you get stuck, just choose one of those things. But now we're starting to see the same things applied over and over again. Yep. J squared acts on jm to give an eigenvalue. Similarly with jz squared, similarly with jz. So let's do this. We're working out n plus or minus. So let me write the jm lightly, because I'm going to cancel it soon. J squared pulls out a j plus 1 h cross squared. The h cross squared, let me bring it through the square root as a h cross. Minus jz will pull out an m h cross. It acts twice, so it'll pull out an m squared, h cross squared. Yep. Minus or plus. H bar, m, h bar. The h bar squared's out here, and here's our m. And this is a number which can come outside the bracket. The bracket would be 1, so it's gone. So we've got an expression for n plus or minus. Yep. This n plus or minus, this normalisation factor is going to be h bar into jj plus 1. And let me put these two terms together as follows. So here we have our normalisation factor n that appears in this expression. We're 80% of the way towards deriving what we want, which is the matrix elements, I'll remind you, of j plus or minus. By the way, this is probably the heaviest lecture in the course, if you hadn't noticed already, because I certainly had. Okay, we want the matrix elements of j plus or minus, which are these things. Now we know that when j plus acts on jm, it raises m by 1. When j minus acts on jm, it lowers it by 1. But there's a normalisation factor that comes out the front, the n plus or minus, which we've calculated as this. Yep. So there's a h bar, which I pull out the front. And then there's that huge square root, which I can also pull out the front. So in here there's a square root of j, etc. So I regret writing that out. Here we have our big square root. And I've dropped that minus.
David, isn't the minus supposed to be on the top rather than the bottom? If you look at the bottom right board.
So if I look at the bottom right board...
As you go from the second last line to the last line, you swap them.
So the minus plus has become a plus minus. I just need to think about that for a second. So this is a plus minus.
So when you expand the bracket.
So when we expand the bracket, this is minus m times m, which is minus m squared. And when we expand the bracket, this is minus m times plus or minus 1, which is minus or plus. Thank you, I should have explained that. So we've pulled out this factor and we're left with this bracket, again because of the orthonormality of the generalised spherical harmonics. This will equal 1 only if j prime equals j, and if m prime equals m plus or minus 1. And because of this latter Kronecker delta, this object, this matrix is not diagonal. So this is equation 247. So we've calculated the matrix elements of j plus or minus. Now we want the matrix elements of jx and jy. Now let's make our life easy, right? Jx equals, so j plus or minus is jx plus ijy or jx minus ijy. So the j plus or minuses are linear combinations of jx's and jy's. Now this is all linear algebra from one perspective. If the j plus and minuses are linear combinations of the matrix element of the jx and jy's, the converse is also true. Jx is a linear combination of j plus and j minus. Yep. So for example, jx would be, if you take j plus and add j minus, the jy terms will cancel. You'll get 2jx, which is fixed up with a half. Since this is linear algebra, if we know the matrix elements of this, we know the matrix elements of this, add them together, divide by 2, and you'll get the matrix elements of j plus. So just to repeat, since this is linear algebra, and this is a linear relationship, the matrix elements of j plus, add it to the matrix element of j minus. We've calculated them both just before. Add them together, divide by 2, and you will get the matrix elements of jx. Similarly, for the matrix elements of j minus, of jy, sorry. So in a sentence, the matrix elements of jx and jy are just a simple linear combination of the matrix elements of j plus and minus, and the explicit expressions are written in equations 250 and 251 respectively. I won't write them down here because I've written enough equations. As you know, I'm not going to write another 30 more. I also want to make the point that Friday's class, there's 2 classes, a lecture and a tute. Both of them will be lectures. So the 2 Friday classes will be lecture 11 and lecture 12 respectively. So let's talk now about spin angular momentum, which I'll just abbreviate to spin. The spin is an angular momentum, and so therefore spin angular momentum is a special case of everything that we've done today. I've already emphasised that the matrix formulation of angular momentum is essential for the theory of spin. But we need a change of notation. Some of this is natural. For example, J is going to become the spin operator S. Jx, Jy and Jz will become Sx, Xsy and Sz respectively. Little j, the general angular momentum quantum number, will become the spin quantum number. Little m, the magnetic quantum number, will now become m subscript s. So this is the spin magnetic quantum number. This will be talking about the projection of spin in a particular direction. Here's a non-trivial or a less trivial change of notation. The generalised spherical harmonics will become spin wave functions, and just because of entrenched history of notation, the spin wave functions are called chi, and those chi's have 2 subscripts, the j, which has now become an s, and the m, which has become an m subscript s. So this is a spin wave function. Again, unlike an ordinary wave function, this has no smearing through space. This object is also called a spinner or a spiner. It's also called a spinner or a spiner. Now we can then take all of the results we've developed commutators for jx, jy, and jz, the expression for j squared, the fact that the generalized spherical harmonics are eigensets of the s squared and sz, the allowed values for j, which are now the allowed values for s, and so on. And we can write them all down in our new notation. And these are written in a bunch of equations that begin with 253 and end with 265. For obvious reasons, I'm not going to write them down here. This is purely a change of notation, but it's a change of notation that you need to be familiar with. So I invite you to spend 5 minutes staring at the equations at the bottom of section 35.1. I invite you to stare at the equations at the bottom of section 35.1 on spin, because you need to be familiar with this notation. Now, I want to give an example in section 35.2, which is for spin 1. Yep. This is to get comfortable with the notation. I'll consider the very important case of spin half in the next class. So for spin 1, our spin wave functions, there's 3 of them. Yep. So the spin is 1. The allowed values of the magnetic contour number will be -1, 0, or 1. This will be the 3 allowed projections of a spin 1 particle, up, down, and sideways. Yep. Remember the hand-waving heuristic model. A spin 1 particle could be doing this. If the z-axis is vertical, it could be doing this. Yep. Sorry, horizontal spinning, or it could be doing this. M equals 1, 0, and -1 respectively. Oh, sorry, ms equals -1, 0, and 1 respectively. Our spin wave functions can be represented as column vectors. So spin 1, projection 1 can be represented as follows. Similarly for 1, 0, and 0, and 1, -1. So these are our 3 spinners in their simplest representation. We could write down matrices for our various operators, such as s squared, sx, sy, and sz. These spin operators, for the theory of spin 1, they're going to be acting on 3 component vectors. So these matrices, in the matrix representation of spin angular momentum for spin 1, these matrices will be 3 by 3 matrices, which again are special cases of our formulas derived for matrix elements. I've written down the 3 by 3 matrices for these 4 operators for spin 1 in equations 268 through 271 respectively. The last question is, how do we represent a wave function? Now this is spin and the spin wave function. The spin can be, in some sense, extended through space. I go here and I might have some spinner, some linear combination of these things, but I go somewhere else and I'll have a different spinner. So let's choose a particular point in space-time. And at that particular point in space-time, the wave function is going to be some complex linear combination of these objects. Yeah? So it'll be some complex number. Let me call it some complex number. Let me call it psi 1 times the first spinner. And at that particular r of that particular t, it's going to be a second complex number, psi 2 times the second spinner. So this complex linear combination of the 3 spinners. I'm using this language now. But if I go to a different point in space at a different instant of time, then these complex numbers change. So this thing is going to be a function of position and time, and so is this, and so is this. So what you end up with is the wave function for a spin 1 system. We're adding together 3 column vectors. They could be shoved into 1 column vector if you want. There's 3 complex wave functions, psi 1. So here I've called them psi 1, 2, and 3. In the notes I've called them psi 1, psi 0, and psi -1. You have 3 wave functions, psi 1, psi 0, and psi -1, both of which are functions of position and time. So we've learned that in the theory of spin, for spin 1 particles, you need 3 complex numbers at each point in space, at each instant of time, to describe the spin 1 wave function. I'll stop there, and thank you as always.